All right, so let's finish this example that we were working on in class a little bit ago. So this is the truss that we were working on, and let's just sort of recap what we had done so far. So this is the truss, the reactions were given, and we spent the majority of time in the example focusing on the method of joints analysis of two joints. We had completed joint analysis of A, and we had gotten our two unknown members A, B, and AD. And then what we had done past that is, if we go to the truss, we could have done joint C because it also has two unknowns, but we went to joint D for the specific reason of making sure that we knew how to use the forces that we had solved. And what I'm getting at is on member AD, because the forces are downward and to the left respectively on the opposite joint, they're up and to the right because of the concept of equal and opposite forces on either end of the member. Remember AD is in compression, so it's on compression on either joint. So you've got to make sure to follow that. So this is where we ended in class. We had solved for 4 of the members, and what we want to do is solve the rest of the truss out. So what I did in the course notebook is I have a line here that says the following was added to the course notebook after class, so you know where we stopped in class and what's going to be just in this video. This is what I have here for joint B. For joint B, so what I did is I went ahead and I drew the joint. I drew the 20 kip load that's acting downward at joint B, and I drew the known forces that we've already solved for. Because we solved for member AB from our analysis of joint A, and we solved for member BD from our analysis of joint B. Now member AB was in tension, so that 24.375 kips is being drawn to the left, and member BD is also in tension, so that's why the forces are left and to the up, and going up. And those are opposite from what are in the joint analyses on the opposing side. So for joint A, for instance, you'll see that force going to the right, for example, for AB. Okay, so we have our joint and we've got our unknowns that we need to solve for. So I'm going to do this somewhat quickly. So we have let's look at our unknowns. We have 2 horizontal unknowns and 1 vertical unknown. So we'll do the sum of forces in the y direction first. And if I've got 2.5 kips going up from BDY, then BEY has to be 17.5 kips going up. So that force right there on BEY is going up. And if BEY is going up, that means that BEX is going to the right. In terms of the slope ratio, what I'm going to say is BEX is going to be BEY times a fraction. And the question is the fraction 3/4 or is it 4/3? And the answer is 3/4 because I'm solving for the horizontal component. So the 3 is associated with the horizontal, so it's 3/4. And 3/4 of 17.5, if you plug and chug, you'll get 13.125 kips. And that's going this way. As for our remaining unknown BC, look at what we've got. We've got 24.5 going to the left, and we only have 24.375 to the left, and we only have 13.125 to the right. We've also got this 1.875 going to the left. So if I look, let's sort of take stock of what we got going on. Which, by the way, if you want to draw the table and list it that way, that's fine. And maybe if you've got a joint with a lot going on, that might be the best way of doing it. I'm not going to do it here, but you can if you want. But I've got 24.375 going to the left, and I've got 1.875 going to the left. That's this force and that force. As for what's going to the right, I only have this, and it's not enough to counteract. So that means BC also has to go to the right. And if you do the math, I've got 24.375 plus 1.875 going to the left, minus the 13.125 going to the right. BC's got to be 13.125 going to the right. And so you should check that out and make sure that you're getting the same answer. I'll erase all these. I don't need those. Okay, so the only thing left we need to do to finish this joint is we need to use the Pythagorean Theorem on member BE. So BEX squared plus BEY squared, and then take the root of that. When you plug and chug that, you get 21.875 kips. So both of these members are in tension. This is 13.125 kips in tension and 21.875 in tension. Now, that is the result of that analysis. I had drawn a lot of the free body diagram and set up a lot of the calculations beforehand, so it's pretty quick. That's the beauty of YouTube. You can always pause and make sure that you're following along with the calculations. And if you have any questions, let me know. Okay, so we only have one joint left that we need to solve, and I'm going to highlight that at the very end when we summarize our answer. But let's go now to our final joint. We've solved. Let me actually scroll up to the truss as a whole. So here's our truss. We've solved joint A, we've solved joint B, or joint D, and then joint B. So we did this joint, did this joint, did this joint, and so now I'm going to focus on our final joint. I'm actually going to solve this joint. The reason why is it's simpler. I have 2 members framing into this joint. I've got 3 members framing into joint E. I only need to solve one of them. It doesn't matter which one, because if you follow along with the truss, I've actually solved for all of the unknowns except for one member, and that's this diagonal member. So that's the only one I have left to solve for. So it really doesn't matter which joint that I solve. I'm just going to do the one that's easier. So I'm going to do joint C. So we did joint A, did joint D, we just did joint B. Now let's look at joint C. So here's joint C. We have our vertical reaction at C, the 17.5 kips, and this BC of 13.125 kips going to the left. We just did that just now at the previous joint. So the only thing we have left are this one, the components of this one diagonal. So I'm actually going to solve for those separately, okay? And I'm going to show you something that's kind of neat. So this is pretty simple. So if I have 17.5 going up, or let's do it in order. Okay, so sum of forces in the x direction. If I've got 13.125 kips going to the left, CE x needs to be 13.125 kips to the right. 13.125 to the left, 13.125 to the right. For CEY, I've got 17.5 going up. I got to have 17.5 going down. So that's just looking at each of these independently. Now what I want to do is 2 things. First off, let's draw the arrows actually on the joint. So CEX is going to the right and CEY is going down. That's your first check. So we solved for the components independently. And then when you compare them, you see that the arrows are pointing in a compatible fashion. If we got that one was going left and the other was going up, that wouldn't make sense with the geometry of this joint. So they both have to either be in tension or they both have to be in compression, and that's happening here. So that's a good check. That's a check to make sure that we did this right. Now, what I want to do is I want to do a little calculation off to the side. Just to show you something. So CEX is 13.125 kips and CEY is 17.5. Watch this. Watch what happens when I take CEX divided by CEY. And when you do this, plug and chug, you will get 0.75. Why that's special is, what is the slope ratio for this member? It's 3 to 4. If you take the horizontal slope ratio divided by the horizontal component of that slope ratio divided by the vertical component of the slope ratio, you also get 0.75. So this is a second check that your truss analysis works. And this will always happen. When you have a truss that has an odd number of members, if you do a method of joints analysis, the last joint will have only one member that needs to be solved for. And if it's a diagonal, it should comport with the slope ratio, okay? Not only that, but the fact that both of the components are either in compression or they're both in tension. So that's sort of an internal check that everything is working. So the fact that these match is very important. Okay, so to solve this out, we just use the Pythagorean Theorem just like we have been. So CEX squared plus CEY squared, take the square root, we get 21 0.875 kips. So this is 21.875 kips. And since they're both pointing towards the joint, they're in compression. And so that's it. One thing I'd like you to do on your homework assignment in terms of reporting the answer is I'd actually like to see the answer like this. So this is the final solution to this truss analysis. We have the truss, we have the reactions, we have the loads, and we have the internal forces inside every member written on the member indicating whether or not they're in tension or compression. It's a nice, concise way of summarizing the entirety of the results of this truss all in one place. Now, one thing I do want to summarize before we finish this video is I want to look at the joints that we analyzed. We started off with joint A, then we did joint D, then we did joint B, then we did joint C. And if you notice, there was one joint we didn't do, and that was joint E. We actually didn't need to solve that joint to solve the entire structure. And more often than not, you don't need to solve every joint in the truss in order to solve the truss. But if we were to look at joint E, what we would find is that since the truss is already solved, we already know all the forces. So the only reason of doing an analysis on joint E would be to do another check on our results. Because if we do an equilibrium analysis on joint E, we should find that the sum of forces in the x direction is 0 and the sum of forces in the y direction is 0. It's not necessary for the scope of the problem, but if you're unsure of your results, you can always do a joint analysis on your final joint to see whether or not the answers are compatible. All right, that's all we have in this video. We will see you all on Friday.